Okay, so last week we just saw the basics of RLC resonant circuits, right? So what we're going to do is this in today's class we'll see how we can use it for impedance matching. So the next today's class and Wednesday's class will be on impedance matching. Okay, and the other thing is a few of you came after class and told me the last couple of classes went pretty fast. The main reason I wanted to cover the introduction much faster. So from this class onwards I'll try to go a lot slower. If anytime you feel I'm going fast, just stop me, ask me to go slower, I will definitely do that. Okay? Okay. Okay. Impedance matching. Right? So, what did we see actually? Before we go there, couple of small corrections, right? I think on the first class we looked at multiple access techniques. So we did DDMA, FDMA, TDD and so on, right? Now OFDM is technically not a multiple access technique. It is actually a digital modulation technique. Okay, so because it is a way to send a signal. So you are given a certain channel. So inside FDMA, you would use OFDM to transmit the signal. You break it up into multiple carriers. But each one of those carriers would all contain information from a single user. So it's really not a multiple access technique. Okay, so that's the first point. The second point is last week we looked at parallel RLC, right? And we looked at the different expressions for Q. And I think one of the expressions we came up with I think some of you corrected me saying it should be real over imaginary, but remember that we are talking about the impedance, not the admittance, right? So for any network, if you look at the input impedance as j omega, you can find an equivalent circuit, right? You can have any frequency, you can make the sum resistance, and let's just call it some R and X, right? It could be at lower frequencies, it could be inductive. At higher frequencies, it could be capacitive. But Q is for the series network. Q is always defined as imaginary part of Z over real part of Z. Okay? But for a parallel network, if you are going to use admittances, then you can also write Q. For example, in this case, it will be R over omega L, or 1 over omega C R, omega C R, and so on. Right? But this expression is valid because for any network, if you look at the input impedance, it doesn't have to be simple parallel RLC. Any network, you can have a resistance and a reactance, right? So this is the correct expression, not the one which I wrote this first in class, corrected it, but this is the correct expression. Okay? Okay. So now we'll look at impedance matching. So why do we want to do impedance matching? We saw that most RF systems use 50 ohms. Okay? So RF systems use 50 ohms as the standard. Okay? Except I think TV systems use 75 ohms. Okay? But majority of them use 50 ohms. So what that means is anytime you interface with anything out which is so anytime you interface, for example, from the IC to the external world, you have to match the circuit to 50 ohms. Okay? Now, of course, the other thing is, it so happens 50 ohms is the approximate trade-off between minimum loss in the system and your max power handling. Okay, it happens to be somewhere in between. So that's the reason why people chose 50 ohms. Okay. Now the other thing to remember is, so okay, if you have a system which is, let's say if you have multiple discrete things, right? Systems, discrete, let's say LNA mixer and so on. If you're trying to match it, so you'll have some power loss because you keep, each time you match to 50 ohms, you'll have some certain power loss in your transmission lines because you're using a certain impedance for those, and you'll have a certain efficiency for each circuit for driving 50 ohms. So this happens to be, so if you try to choose a minimum loss case, then it may not be so efficient, right? And it may not be so, rather it will be very efficient, but it may not be able to handle large amounts of power. Whereas, if you want to transmit as much power as possible, 50 ohms happens to not be the optimum impedance. You would want to use closer to 75 actually, it turns out. So that's the reason why your TV systems use 75. This is not power transfer actually, it's power handling capability, not power transfer. Are you talking about this one, impedance? Actually, this has nothing to do. This just happens to be the. Sure. Absolutely. That's right. That's right. So we end up taking it somewhere in between. Okay. Okay. So the thing is, remember that you have to okay. So depending on the impedance, you'll have to have a certain swing, and based on your power supplies and stuff, actually in general, the lower the impedance, the higher the power handling capability, right? So you'll be able to, for smaller voltages, you'll be able to transmit larger powers. So definitely that is one input into how you choose your standard impedance. Of course, the other one is how efficient obviously the lower the impedance goes, your circuit also finds it actually harder. If you remember your output stages, right? The lower the impedance, actually the tougher it is to drive those. So obviously there's an optimum point which will be the best for for matching multiple stages, because overall for the overall system you got to look at these 2 points. Okay. But you have to remember, ICs don't like 50 ohms, right? Because in reality 50 ohms is actually as far as ICs are concerned, they are actually a very low impedance. Okay, so if you look at MOSFET output impedance, for example, they are typically in kilo ohms, tens of kilo ohms, and so on, right? So in general, to drive 50 ohms, you need a lot of power. So inside the chip, you prefer not to match with 50 ohms. When you are interfacing with the external world, you can't do anything, right? You have to match it with this. That's the standard. Okay. So where do you match this? So LNA input, and so you have 2 options, right? If you have either a driver amplifier which outputs a certain amount of power to 50 ohms, and then that is matched to the power amplifier which is usually on a separate chip. Okay, and that is what drives the antenna. So that is one option. Or some of the newer cases, they are trying to integrate the power amplifier inside your IC itself. Okay, so one of these two will be driving 250 ohms. Okay, one of these two outputs. Okay, DA is driver amplifier. It's something which is driving. It's an amplifier which is it's an output stage which is actually driving your power amplifier. Okay. Okay. So now we'll go back. So we looked at parallel resonance circuits, and series is very similar, right? So we just quickly looked at it and we just skipped it. I would definitely encourage you to try a quick, whatever calculations we did for your parallel network, you should definitely try it for the series network. You'll see it will be very similar, except it will be instead of R or Q equals R over omega I, you'll get omega L over R and so on. But if you look at most real cases, I think we looked at this briefly. So let's say you have a network like this, right? You have L, R and C. So this is obviously neither parallel nor series, right? So how would you analyze this? So this is what you would do, right? You would convert this to an equivalent network. Okay? In this case, it happens to be easy to do this. So let's say we take this portion of the network and we do what is called a series to parallel conversion. Okay? So what you do is you try to find out, let's say, let me call this LP and RP, and let's say this is LS and RS and LS. Okay, so these are the series equivalents. This is the parallel equivalent. Now note that you do this conversion only at resonance, not for all frequencies. Because if you really want to do it for all frequencies, you'll probably get some frequency dependent terms, right? It will be a little bit more complicated. But close to resonance, you can make some approximations. Okay? So let's see. So what is the impedance here? Rs plus j omega Ls. That is the impedance here. So you know these two networks are equivalent. So what we'll do is we'll look at the impedances in both cases and equate them, equate the real and imaginary parts and find out what it gives us. So you want to find out LP in terms of Ls, RP in terms of Rs. Okay? So what is this equal to? So you want to find out these two, right? So it's RP times omega LP over RP plus. Actually, what we'll do is we'll use omega naught because it's very close to resonance. At resonance. So what is this? Let's just simplify this further. So you have omega naught LP whole squared times RP. So what you do is you just obviously multiply the numerator and denominator by the conjugate in the denominator, right? Over. Okay, so pretty straightforward, right? Okay, now what we do? Well, what do we do? We equate the real and imaginary parts. So let's try equating the real parts first. So Rs is over okay. Now let's try to rearrange this in terms of parameters we know, right? What do we know? We know that Q for the, let's say take the parallel network. What is that? RP over omega naught LP. Okay, but remember, so this is, let's call it QP. Obviously, this also has to be equal to QS equals to, let's just call it Q. Because obviously the two networks are equivalent, the Qs also have to be equivalent, right? And of course, QS happens to be omega naught Ls over Rs, okay? It just happens to be that, obviously for the series network. Okay, so now let's simplify Rs in terms of Q, right? So what is this? What we'll do is, let me go back to the previous page. So we'll take this, divide numerator and denominator by omega naught LP the whole square. Okay? So what does it give us? Obviously numerator will remain RP over, this will become 1 plus, so by 1 plus, oops, sorry, my palette is gone, but okay. You have a question? Yes, definitely. Omega naught Ls by Rs. So this is one part of the homework which I want you to do. Okay, sorry. Okay, maybe I should have said that. I thought we covered it last week. Let me see. Maybe we just went through it very fast. I don't remember if we did this. Okay, looks like we didn't do it. But okay, so let's just remember that Q for a omega naught L by Rs also equal to, okay. So for a series network, for a parallel network, it is RP over omega naught LP, R over omega naught L, and or 1 over omega naught CR, right? For a series network, it happens to be omega naught L over R, or which is obviously, you know that omega naught L is 1 over omega naught C at resonance. So it happens to be 1 over omega naught CRS, CSRS if you want it that way. Okay? So that's why QS is omega naught Ls over Rs. And remember, I think we just did this at the beginning of class, that is, if you have any network, right, R plus Jx, the Q is imaginary part over real part. In our case, we have R omega naught Ls. Right? So it's omega naught Ls over R. Okay? And what is this? This is nothing but RP over 1 plus Q square. simple this thing, right? Expression. So in other words, yeah, you can think of it as RP equals RS into 1 plus Q square. So this is the result we want, right? We are trying to find RP in terms of RS. Okay? Okay, so let's look at the imaginary part, right? Okay, so let's go back and look at the imaginary part. Sorry. What is the imaginary part? On the left side is j omega naught ls, and on the right side it is this portion, j omega naught lp rp squared over rp squared plus j omega naught lp squared. So what we'll do is we'll equate those also. Omega naught ls equals right. Then what we'll do is, obviously we can ignore the omega naught for now, this one. And again we'll do exactly the same thing, right? We'll, on the right side, we'll divide the numerator and denominator by omega naught lp. What does that give you? So ls, so now we've cancelled omega naught. So ls is lp times, sorry, should have gone to this. LP times good. It's pretty straightforward, right? Okay. So, and what is this? Q square over 1 plus Q square. Everybody understood that? Okay. So what that means is LP is Lx into 1 plus Q square over Q square. Okay. So this is the second thing we should have. And also note that in many cases you will find that if Q is very high, 1 plus Q square over Q square is almost 1, right? Which means LP is almost the same as LS. But if you go back, if Q is very high, RP is much higher than RS. Okay? Just keep that in mind. So what I want you to try out at home is a similar case. Let's call this homework. It's not a, you don't have to turn it in or anything, but I want you to try this out when you have some time. It should take 10 minutes, not more than that, right? What I want you to do is, if you have this case, RS, ES, and let's just call it L, right? Of course, we saw that the capacitance, nothing happened to the capacitance in the previous case. I want you to try this. You should convert this to RP, CP, and L, right? I want you to convince yourself that RP is again RS into 1 plus Q square. Okay, and CP is CS into Q square over 1 plus Q square. It's just a little bit different from the LP relation. LP relation, you have 1 plus Q square over Q square. Here you have Q squared over 1 plus Q squared. Okay? Is that pretty straightforward, everybody? Okay. So yeah, so in other words, you can write, I guess you can write XP as XS into 1 plus Q squared over Q squared. It so happens that, XP for a capacitor is 1 over, omega Cp and so on, right? 1 over J omega Cp. Okay, so this is a general relation for any reactance. Okay. Now, we'll just do a small refresh. refresher for actually let's call it max power transfer. Yes. Which one? The first one? Okay. The resonant frequencies? Resonant frequencies will be identical. Will be identical for the two. In fact, you are trying to equate the two circuits at resonance, right? Yes. Yes. So, the actual resonance happens at C in parallel with LP, not with LS. That will be the actual resonant frequency. See, remember that this is a complex resonant this thing, right? We looked at purely series and purely parallel. What you don't know is how the circuit will behave. What you try to do is assume a frequency of resonance omega naught and do all the calculations and try to convert it to either a parallel or a series for any network you find. And the resonant frequency will be defined by this either the parallel or the series network, whichever one you convert it to. Okay. In this case, of course, because one circuit happened to be in shunt, it's a lot easier to convert it to a parallel network. Okay. Yes. So the reason is first of all, of course, you are interested in the frequency range around resonance. But more importantly, remember that you have taken your Q at resonance to be omega naught LP over RP, right? So that definition is valid for you can define something when you neglect. For example, if you look at very low frequencies, you can neglect C, for example, and just take LP RP. You can do the same thing. Definitely, it will be generally valid. But in this case, we are looking at the Q at resonance and defining everything in terms of that. You are right. It will be valid at any frequency, right? But actually, you have to be a little bit careful. It will be valid, not necessarily at all frequencies. Actually, I'm wrong. It will not be valid at far away from resonance. Yes. But we are using only omega naught. Okay. Sure, you can do that, but the difference is Q tends to vary a lot over frequency. Right? Sure, if you take much lower Qs, you'll do it, you'll get it. But the difference is, okay, so what you would do is, you're going to use, let's say you're going to use this for a certain frequency, right? So what you would do is, you would take the Q at that frequency and calculate this network at that frequency. What happens is, remember, if you just take the overall input impedance of this, right? And if you try to convert it to look at the real and imaginary parts of the, let's say, the admittance, they are going to be frequency dependent. And that is the reason why what you're saying is right if you take into account that LP and RP will be frequency dependent terms. We are trying to find frequency independent terms, right? You're right. I mean, any network you take, you can find an input impedance which will in general depend on frequency, right? So you are trying to find out simpler networks, right, around resonance. Did everybody get that? Right? In general, they are going to be frequency dependent, right? Yes. Yes, it will be valid. So what is the Q? Okay, so what is RP? RP is infinity. Okay, so you have lost that. What is LP? What is let's go back here. What is LP? If Q is infinite, what is LP? So it's a trivial case where you don't transform the network at all, right? It's just a simple LC parallel. Sorry? Yes. 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 It will be slightly deviant. Definitely. Yes. Yes. You will see that. Because whenever you have a finite Q, you will see that. Yes. That's right. So that's what you are trying to find. You are trying to find around resonance some circuit equivalent, some simple circuit equivalent. Okay. So that is the idea. Okay, so you people remember what maximum power transfer theorem is, right? So actually let's call this ZS, ZS. Okay, so ZS is RS plus JHS. So what is the condition for maximum power transfer? Yeah, so ZS equals ZL conjugate, right? So obviously what this means is RS equals RL and XS equals minus XL, right? You remember this? So, yeah, so this is pretty. So what we are going to do is we are going to look at ways to reach this optimum impedances. Realize these optimum impedances. Okay. So if you look at impedance matching, right? Traditional microwave. What do you? Does anybody remember what kind of matching can be done? Okay, so stub matching. Stubs. Okay, so the other thing is quarter wave transformers. Right? So those are the. Which one is? So which is why it's a good question. So obviously you are given a usually what the way you would do it is you're trying to vary ZL, you're given ZS and DS, right? Isn't that right? So obviously what happens if you try to vary ZS? What is the maximum power transfer if you can vary ZS? Let's say your ZL is fixed and you are varying ZS. What is the maximum power transfer that can be transferred to ZL? 100%, but what is the condition? ZS is 0, right? Obviously both RS and JXS is 0, gives you maximum power transfer because you can get the total voltage PS across the load. So that is, that is a trivial case. Trivial as in, it's trivial, but it's not so intuitive to many people. You have to know which one you are varying. Good point. That's right. Okay? And of course, you can also use series lines, right? Okay, so that is traditional. So what you would do is, lambda by 4 transformer, what does it give? So let's say, so you have a lambda by 4 transmission time, and you have the ZL. What is ZL in terms of ZL? Anybody remembers? Right? So this is for the lambda by 4 case. And in this case, you have to use a Smith chart. You have to find out each time you are at a certain transmission line. You see where you go on the Smith chart, and finally you know the initial point. You know the initial point. You know the final point. You want to go there in some certain way, right? You may go using inductors, capacitors, whatever, right? Okay. So now let's look at the more what we use in ICs, right? We tend to use lump matching. Okay. So what that means is, obviously real estate is very important, very expensive on ICs. You can't have transmission lines millimeters and centimeters and so on. Okay. So if you have a PCB, for example, you could do that because it's much cheaper. Okay. So what you would try to do is realize the same, let's say, inductance, capacitance using lump elements. So let's look at the first case. So let's look at upward transformation. Okay. So let's say you are given a load resistance of 50 ohms. You want to transform it to 200 ohms. So one way is to do something like this. You want for 200 ohms here, and let's say this is 50 ohms, and network we just looked at a few minutes ago. So what is, how do you do it? So this is actually called a low pass L match. Okay, it's called an L match because you have two elements, and you have one element vertical, other element horizontal, right? That looks like an L in different orientations. It's called an L match. And why is it low pass? Obviously, at low frequencies, capacitance is an open circuit, inductance is a short circuit. You transfer all the power from input to output. If you go to very high frequencies, obviously inductor is an open circuit, capacitor is a short circuit. You short circuit all your signal to ground, nothing will go to the outside. Okay? So what do we know from this? We know that we can transform it to RP, LP, and C. Okay? And we know the equations governing this, right? So we know LP is Ls into 1 plus Q squared over Q squared, right? And more importantly, we know RP is Rs into So what do we know here? We know RP, we know RS, don't we? What is RP? Actually, let's rewrite this slightly because we don't know the Q so far, right? So what we're going to do is RP over RS minus 1, right? Make sure to remember this expression. Yes. How would you match at all frequencies? It could be either. You could put it inside the chip, it could be off chip. Right? It could be either. Right? But typically, what we will look at is, we will look at cases where we will try to put them on chip. Obviously, if some values get too large, you will be forced to put them off chip. Okay, so let's say you don't put it at all. What happens? Why do you want to do this matching from 50 to 200? Let's say you have an amplifier here whose output impedance is 200 ohms. We just looked at maximum power transfer, right? So we have, let's say, an output impedance of 200 ohms for the amplifier. Let's say the driver amplifier. But you have to drive 50 ohms off chip, right? The best way to transfer maximum amount of energy is to match the 50 ohms up to 200 ohms and drive the 200 ohms. So you get maximum power transfer. Yes. Yes. Yes, absolutely, that's right. Yes, you cannot use this, but you can, because remember that one of the definitions of Q is omega naught over bandwidth. So if you have a wideband signal coming through, what that means for you is you have to have a very low Q, right? You have to have a very low Q match. Okay, that's what it means. Okay, so this, of course, so this is the general expression for a lot of L matches. That's what you'll see. Okay, now what do we know here? What are RP and RS? What is RS? I think that's easier, right? In this case, what is RS? 50 ohms, right? What is RP? Right? It's 200 ohms, right? Remember, we're trying to convert the series to parallel, and at resonance, this LC will not, this LC will resonate at the frequency of interest, and you'll have only RP. That's the input impedance. Is that right? Okay. So what does this mean? It's actually a fairly low Q. Okay. So now the other things we want to know is we want to find out. Let's go back to the previous page. What we'll do is we know this resonates at f naught or omega naught, right? So what we'll do is we'll work backwards because what we are interested in finally is this network. Okay. So we'll use two conditions. One, of course, is fine. We know RP and RS, so we found out Q, right? Once we find out Q, what we're going to do is we're going to find out using this information that we wanted at a particular frequency. We're going to calculate LP and C, and then we'll work backwards. We know the relationship between LP and LS, and we'll back calculate LS. Okay. So let's see how that works out. Okay. So you know that Q is for the parallel network is RP over omega naught LP. Okay, so what this means is LP is RP over omega naught Q. Right, pretty straightforward. And what do you know? You know Q, which is root 3 in this case. Omega naught, so let's say you want to match it at a certain frequency. Right? So you know omega naught. And you know RP. RP is known to us. So you can automatically find out LP. Very straightforward. Right? So let's call this equation number 2. Why does this keep happening? Sorry? Oh, it is the hand touching. Okay. I'll be careful. So let's call this equation number 1. Okay. This is equation number 2, right? What is equation number 3? We know LS is LP into Q squared over 1 plus Q squared. Right? So now you found out LS. Okay? Then what do you do? What is C? C is 1 over LP omega naught squared. So these are the 4 equations you're going to find out, or you're going to use to find out LS, C, right? LS and C. Okay? Okay. So let's do a simple match, right? So we calculated, so let's do the same thing at, let's take the sample frequency, 2.4 gigahertz. Okay? So what do we know? So again, let's say 50 to 200. Okay. So now, first we'll do. So we know that Q is root 3, right? We just calculated that. So what this means is, next step, calculate LP. Right? LP is 200 over straightforward, and it comes out to approximately around 7.7 nanometers. Okay, so that's step number 2. What is step number 3? LS is LP times squared over 1 plus Q squared. So it's going to be slightly lesser than, because in this case Q is very low, right? You see that LS is fairly different. In this case it happens to be 5.75 nanometers. So obviously if the Q was higher, it will get closer and closer to LP. Okay? And finally, what's the 4th step? C is, in this case it happens to be 0.57 picofarad. Okay, so what do we know? Let's go back to your network. So what do we know? This is 5.75 nanohenry, and this is 0.57 picofarads. Okay, these are pretty practical values actually for implementing on-chip matching. Because remember, we talked about this last week. Anywhere from a couple of hundred picohenries to several nanohenries is easily possible on chip. And similarly, several tens of femtofarads to several tens of picofarads, sometimes even hundreds of picofarads if needed, are possible on chip values. So these are pretty decent values. Okay. So now let's look at a different kind of transformation circuit. So we'll do the same thing, except we are going to look at what is called the high pass. Okay, so this is called the high pass L match. Okay. So what would you do? Convert this to RP, CP and same L. Right? And we know the equations governing this, right? Cp is Cs into Q squared over 1 plus Q squared, and we know Rp is Rs into, rather I know, you are going to know when you do your homework, right? So these are the two, we just looked at it just now, right? These are the two relationships. So what does it give you? Again, it gives you the same two relations, right? Root of Rp over Rs minus 1. Okay, so let us do the exact same thing. Let us do an example. Same thing, we want to do 50 ohms to 200 ohms at 2.4 gigahertz. Okay, we'll do the exact same example and find out what values it gives us. What is the Q? Root 3. Right? It has to be the same. The relationship, the impedances are the same, so Q has to be the same. Okay, Q is again the same. Then what do you know? You also know that Q is omega naught CPRP for the parallel network. Is that right? So what that means is you can find CP is Q over omega naught RP. So you know omega naught, you know RP, you know Q. So you can calculate this. Okay. So it's 1.73 over, 212 times 200. Right. So this works out to 0.57 picofarads. Okay. Now let's use the next equation, equation number 3, which is Cs equals Cp into 1 plus Q squared over Q squared. Because remember, this is actually Cp. What we want to find out is Cs, right? It just so happens that it came to the same value, right? 0.57. But you really want to find out Cs. So Cs happens to be larger, 0.76 picofarads. Okay. Okay. So then next step, what is the next step? Find out L. 1 over omega naught squared Cp. Is that right? this happens to be 7.66 nanometers. Okay. So now we have found out L, we have found out CS, and so this happens to be and this happens to be, I think, 0.765, right? Okay, 0.765. So these are the other two values. Okay. So now, how would you know which network to use? How would you choose it? So now we looked at two options, right? One is the low pass, the other is the high pass. Which one do you want to use? And why? Okay. So what is the number one choice for many people would be die area, especially if you're going for an L match. Okay. The reason is the inductor values are quite different, right? One is 5.75, the other is 7.67. So smaller inductor is always better, right? The reason is you would use lesser die area, and one more reason is many of these inductors are not ideal inductors when you look at on-chip values. Okay, so what that means is if you use a smaller inductor, it is quite possible that your losses might be lower. Okay, we'll look at it. We'll look at it in a couple of classes. We'll look at how to design on-chip inductors. Okay. Then of course, quality of match versus frequency, right? So let's look at what the match could look like, right? So let's say it looks something like this. So low pass match could look like this, and a high pass match could very well look like this, something like this. Yes. I'm not talking, okay. So what I'm saying is, so you are interested in a certain band around 2.4, right? So your quality factor of the matching network decides how much, how well it's matched around 2.4. But suppose you are interested in characteristics outside 2.4. Outside, let's say earlier you are interested in a 200 megahertz, let's say a 200 megahertz bandwidth or 100 megahertz bandwidth around 2.4. But you may also be worried about, for example, let's take the case of, let's say you have the second harmonic, 5.8, right? You want to make sure you're not transmitting at 5.8 because 5.8 may be close to some other band, somebody else might be using it, right? In which case, what you try to do is, you try to do a low pass match, which will give you better matching at higher frequencies. Okay? That is the other consideration. Yeah, I'm just coming to that. So y-axis is your reflection coefficient. Okay, and let's say this is the 0 dB point. And this would be high pass. So in general, you should remember that is a good number to choose. Okay, or S11 is, remember, it's the same as or almost the same as the reflection coefficient. Okay, so it's a good idea to do your matching such that your S parameter value is reflection coefficient is less than minus 10 dB. Okay, so let's say your minus 10 dB was somewhere here. Okay, let's use a different color. Right? So even inside this, you could get a different portions of the network could match at minus 10. If you look at the minus 10 point. Okay? Okay. Now the third thing is parasiticles. Okay. For example, you're trying to, let's say, drive something off chip, right? That's what we've been looking at. Okay. I don't know if you people know about a little bit about IC technology. Some of you, I'm sure, know. But coming out of the IC, right? You have the circuit. Then you have what is called a bond wire. You put a pad. You have a bond wire which goes from the pad to the external lead. So all those things add inductive parasiticles. Okay. So what you could try to do. So your circuit becomes more and more complicated. If you go back to your, let us take this case, right? The second case. If you have any series inductances here before your 50 ohms, so you have L, CS, and you have another series inductance that tends to cancel out your CS. What that means is if you have inductance, to get the same matching, you need to have a larger capacitance to compensate for that. So you might be better off going for the earlier match. What is that? If I can find that. You may be better off going for this. Why? Let's say your bond wire inductance is a couple of nanometers. You actually want 5.75. So what you would do is, you design an inductor actually for 3.75. Get the extra 2 for free from your bond wire. So that way you will get an even smaller inductor. Okay? And I guess one last thing is, we have a couple of minutes, right? Okay. We'll just quickly go through. How would you match to a complex load? So the way you would match to a complex load is, you have 50 and let's say you have some capacitance CL, right? So what you would try to do is, you would try to do it such that, sorry. So let's say you're trying to do this match, right? What you would do is, you combine these two guys and get an effective series capacitance, right? And that would actually make the actual match. So let's say this is CS, this is CL, you get an actual CS prime, right? And you're going to design for the CS prime instead of CS, and then you'll back calculate your value of CS. Okay? Okay, so for now we'll just stop here. I think I had a little bit more planned, but we'll quickly look at it in next class. Okay, we'll stop here.